Greetings to Prof. 1 Azina. We are from Group 4, and now we would like to present our mini project, which is Shell M2 Heat Exchanger Design. And our group member is me, SHIM with mention number 216913, Muhammad Aziz with mention number 214259, MARSHA Anna Andrew with mention number 215540, No ALISHA FATHIN with mention number 214398. And here is the content of our presentation today. The first one is case study. Second is introduction, literature review, process description, heat exchanger design, schematic drawing, simulation, prototype, cost estimation, and the last one is safety and recommendation.
So we proceed to the case study. In this study, the hot oil is cooled with water by using a heat exchanger to achieve the desired final temperature of the oil. So one shell and two tubes make up the shell and tube heat exchanger that we are using. We are required to calculate the NTU value, therefore we will use the effectiveness NTU method for the calculation, and we also need to find out the surface area of the heat exchanger. For introduction, a heat exchanger is an instrument or device that moves heat from a fluid with a higher temperature to one with a lower temperature. The two fluids are kept apart within by the solid wall. Heat exchanger can categorize according to their construction and flow. Heat exchangers can be divided into the three categories based on how they made: shell and tube heat exchanger, plate type heat exchanger, and air-cooled heat exchanger. They can also be categorized as cross counter or parallel flow depending on the direction of flow. The application and the available pipe connection in the process plant determine the construction and flow circuiting options. In this project, oil and water have been chosen as the raw material. According to our case study, we are using the shell and tube exchanger to cool down the oil. The next part is literature review. The design and analysis of heat exchanger, especially the shell and tube type, are important for optimizing heat transfer efficiency. Different types of materials for tubes, as well as the presence of buffers, can significantly affect the heat transfer rates and overall performance of the heat exchanger. Overall performance and mechanical design consideration are necessary to ensure the effectiveness and reliability of heat exchanger in industrial application. This exchanger consists of tubes that act as flow channel for one of the fluids and a shell that holds the tube bundle and serve as a conduct for the other fluid. The design of tube type heat exchanger involves iterative process and trial and error methods to achieve optimal heat transfer areas. In the presented case study, the focus is on designing an oil cooler specifically for a shell and tube heat exchanger with buffer to induce turbulence and enhance heat transfer coefficient. The case study illustrates the importance of proper design consideration and analysis in optimizing the performance of shell and tube heat exchanger. The next part is introduction of shell and tube exchanger. Shell and tube exchanger consists of large cylinder shell with a bundle of smaller tube inside. So we move to the process description. This first is the objective of this process is to efficiently cool a hot oil heat exchanger using room temperature water as a cooling medium. This hot oil heat exchanger is aimed to cool down 20 kg per second of hot oil by using 90 kg per second room temperature water. Hence, a high efficiency of heat transfer is needed to ensure the target achieved. A one-shell, two-tube pass heat exchanger is picked due to the high thermal efficiency that able to cool down the hot oil from 80 to 65 degree. The room temperature water passes over the tube and thus act as cooling medium to cool down the oil. Lastly, the effectiveness of heat exchanger will be calculated by NTU method to know its performance.
So next we goes to the advantages of shell and tube heat exchangers. Firstly, it has high thermal efficiency due to the counter flow and the presence of buffer inside. And the second is it produces less pressure drop compared to black heat exchangers. The third one is cheaper than the flat heat exchangers as well. And the fourth is easy to maintain and repair. And the fourth is also can be used in system with higher operating temperature and pressure. And next we goes to its disadvantages. The firstly is the capacity of the tube cooler cannot be increased because the size of tube in the heat exchangers is fixed to there. And the second is require more space in comparison to plate cooler due to its bigger size. And the third is overtime vibration may damage the heat exchangers. And the fourth is cleaning and maintenance is difficult since a tube cooler require enough coolants to remove the tube nest. For the heat exchanger design, we are using two methods for our design. The first one is LNTD methods, which is used to calculate the total area of heat transfer. And the cross method is to calculate the other dimension in our heat exchangers. And the second one is NTU methods, which is used to calculate the effectiveness and the performance of our heat exchangers. So for our mini project, our group is picking the question 11 and 101 in page 702 in our textbook as our question today. And our in the question, there is two input here. The first one is hot oil and the second is cooling water. So the initial temperature of the hot oil is 80 degrees Celsius and its final temperature is 65 degrees Celsius and its mass flow rate is equal to 20 kilogram per second and its thermal conductivity is equal to 0.1398 watt per meter per Kelvin. And for the room temperature water, its initial temperature is 25 degrees Celsius and its final temperature is equal to 25.43 degrees Celsius and its mass flow rate is 90 kilogram per second and its thermal conductivity is 0.619 watt per meter per Kelvin. So here is the some other information given by the question. The first one is the overall heat transfer coefficient, which is U equal to 225 watt per meter square per degree Celsius. And our heat exchanger will be one shell, two tube pass heat exchangers. And the flow is counter flow. For your information, the mass flow rate given is scale up because the mass flow rate given by the question is too small, which is about just around 2 kilogram per second. So we scale out them. So here is an assumption we make to ease our calculation. The first one is steady operating condition exit, and the second is the heat exchanger is well isolated with no heat loss. And the third is change in kinetic and potential energy of the fluid stream are negligible. The fourth is no falling. Fifth is fluid properties are constant. So now I will explain the heat exchanger design calculation. So the table in the left-hand side is the extra information we find from journal, which is for the information for tubes only. The length of tubes, internal diameter, external diameter, clearance, material of tubes, which is copper, and its conductivity, thermal conductivity, and type of pitch, which is square pitch. So first thing first, we calculate the number of tubes. We divide the actual total heat transfer area with the area of single tubes, and finally we get the 90 tubes. So for your information, the total heat transfer areas is we get from LNTB method, which I will show and explain the calculation way later. Yeah, and the second one, we calculate the tube pitch. And here is the table that we find from the textbook. And since we use the tube square pitch, so we use the second table only. So the tube pitch will equal to 1.25 external diameter. So finally, we get 0.03125 meters. So next, we calculate the bladder diameter. And the K1 and N1 is fine from the table, the previous table. So since we are using the two tube pass, so our K1 is equal to 0.156 and our N1 is equal to 2.291. So after substitute in the equation, we get our bladder diameter equal to 0.4 meter. So the next is shell diameter. We are using the Kerr method. ds equal to db plus clearance. DS stand for the shear diameter and DB is stand for the bundle diameter and KLS is for the journal. So after substitute this all, we get the shell diameter equal to 0.4077 meters. And next, we calculate the number of chamber. The number of chamber equal to length of tubes divided by the minimum buffer spacing. The minimum buffer spacing, we just use the 0.2 times the length of tubes because, this calculation is based on the journal. Yeah. And finally, we have 5 chambers. So next, we're calculating the actual buffer spacing. And the buffer spacing will equal to the length of the tubes divided by the number of chamber. And finally, we get the 0.43 meters. And next will be shell cross-section area. And we substitute it, the information we calculate previously. And finally, we get our shell cross-sectional area will equal to 0.035 meters square.
So now I will present the summary of design of our heat exchanger. So our heat exchanger consists of one shell pass and two tube passes, and this has counter flow heat exchanger because counter flow can pursue higher heat transfer performance, and the overall heat transfer coefficient is 225 watt per meter square per degree Celsius. And the total surface area of our heat exchanger is 15.226 meters square, while for the tubes, the length of the tube is 2.50 meter. The internal diameter of the tube is 0.022 meter. The external diameter for the tube is 0.025 meter. So thus the worthiness for the tubes is 0.003 meter. The external area per tube is 0.00049 meter. The number of tubes in our heat exchanger is 90. The metal used is copper because copper has higher thermal conductivity, and it is resistant to corrosion. The thermal conductivity of copper is 335, which is I said earlier. It is high, so it can withstand the higher temperature. While for the shell diameter is 0.41 meter. The clearance of the shell is 0.0063 meter. The cross-sectional area is 0.035 meter. And the equivalent diameter for shell is 0.0246 meter. While for the baffle, is functioned to support the tube in the proper position. And second, baffle can guide the flow of the shell side. And now we move to the pitch. So our heat exchanger has square pitch types, and the tube pitch ratio is 0.03125 meter, and the bundle diameter is 0.40 meter. Next is schematic diagram. This diagram is done by drawing in AutoCAD. As you can see from the slide, the oil and water will enter the heat exchanger from opposite direction since our design is counterflow. The oil will enter heat exchanger from the left top and will come out at the right bottom of the heat exchanger. The blue arrow shows the flow of oil. In case you are wondering why the flow of the oil is like this, it is because the presence of baffle, which prevent the oil from flowing linearly. While for the water, it will enter from the right top of heat exchanger and will come out at right bottom next to the oil outlet. As the water enter the heat exchanger, it will then enter the tube and flow along the tube. Upon reaching the tube sheet, it will make like a U-turn and enter the tube of the second pass before coming out. The black arrow shows the flow of water. It has to be noted that the oil and water will never mix since it is separated by tube sheet and tube bundle. From the diagram also, we can see the cross-section view of the exchanger. From there, we can see clearly how it looks like from the inside. The internal and external diameter of the tube is 0.022 meter and 0.025 meter respectively. Next is the baffle section view. The baffle length is about 70% from the diameter of the shell. That is 0.26 meter, and its outside diameter is 0.40 meter.
So now we use the LNTV method to calculate the total heat transfer area and the NTU method to calculate the effectiveness and the performance of the heat exchanger that we design. So first thing first, we calculate the temperature change and the maximum temperature change. So since our flow is in counter flow, so the change in T1 will be equal to temperature of hot oil inlet minus with the temperature of cooling water outlet, which will be equal to 54.57 degrees Celsius. And the change in T2 will be equal to temperature of hot oil outlet minus with the temperature of cooling water inlet, which will be 40 degrees Celsius. And the maximum temperature change will be equal to temperature of hot oil inlet minus with the cooling water temperature of cooling water inlet. And it will be 55 degrees Celsius. And then we calculate the log mean temperature. And for here, we just substitute the change in temperature one and the change in T2 into the equation. Then we get the log mean temperature equal to 46.91. And then we calculate the heat capacity. For the hot oil, the heat capacity will equal to 40.12 kilowatt per Kelvin. And for the cooling water, the heat capacity will be equal to 376.2 kilowatt per Kelvin. So from here, we know the maximum heat capacity will equal to the heat capacity of cooling water. And the minimum heat capacity will be equal to the heat capacity for hot oil. And then we calculate the capacity ratio, which equal to the minimum heat capacity divided by the maximum heat capacity. Then we got 0.1066. And then we calculate the rate of heat transfer. Yeah, and the rate of heat transfer will be equal to 160.71 kilowatt. And the maximum heat transfer will be equal to 2206.6 kilowatt. And then we are able to calculate the effectiveness, which equal to the rate of heat transfer divided by the maximum rate of heat transfer. And then we got the 7. Our effectiveness is 7%. And for information, the effectiveness is equal to the effectiveness one in one shell pass, which is we are referring from the textbook. And next, we calculate the surface area. The surface area equal to the rate of heat transfer divided by the U and the log mean temperature. Then we got our surface area is equal to 15.23 meters square. And then we are able to calculate our NTU. And since we are using the one shell two tube pass, so we are using this equation. So we just substitute this equation, then we got our NTU one equal to 0.07593. So after calculating all the stuff, we are able to simulate the heat exchanger. So here is the effectiveness against with the mass of cooling water. So from the graph, we could see that when the mass of cooling water inlet increase, then our effectiveness will increase as well. So here is the simulation for NTU against with the mass of cooling water. So similar with the previous one, when the mass of cooling water inlet increase, then the NTU will increase as well. So for here, we could conclude that when the mass of cooling water inlet increase, then the performance or our heat exchanger effectiveness will increase as well. So here is the costing estimation. So first one is the price of tubes. The total price of tubes is equal to 8,030 ringgit Malaysia with 53 cents. And the second one is tube sheet. The total price is equal to 37.12 ringgit Malaysia. And for the buffer, the total price is equal to 1,121.63 ringgit Malaysia. And for the shell, the total price is equal to 1,440 ringgit Malaysia. So for our heat exchanger, the total price will be 9,507 ringgit Malaysia with 66 cents.
So I'm Marsha and I will now go over our group's heat exchanger 3D prototype. As we can see from the picture pasted in this slide and the prototype that I'm holding right now, we have created the shell and tube heat exchanger, which consists of one shell and two tube passes based on the case study that we have chosen. The water bottle itself represents the shell, whereas the sticks inside the shell or water bottle represent the tube passes. This is one pass and this is the other pass. This is where the heat transfer and fluid flows occurs. Furthermore, there are 5 short sticks were placed between the tubes, and these 5 short sticks represent the baffle, which is used to direct the fluid flow and support the tubes. Move to the next part. The stick on the front part here is the divider between the water inlet and outlet. Since this stick is the divider between the water inlet and outlet, therefore the tube with green color here is for the flow of the water. The top green tube is the water inlet, whereas the bottom green tube here represent the water outlet. Next, as we can see, there are two green kinds of like walls placed between the buses. So these green walls are the tube sheets in the shell and tube heat exchanger. The tube sheets are used to prevent the mixing of the fluid on the shell side and the fluid on the side of the tube. Move to the last part. The tube with no color here and here represents the oil inlet and outlet. The top tube is the oil inlet while the bottom tube here is the oil outlet.
Here are some key safety and environmental issues associated with heat exchanger. The first one is corrosion and material compatibility. Heat exchangers are often exposed to corrosive environments due to the nature of the fluid they handle. Corrosion can compromise the integrity of the heat exchanger, leading to leaks and potential safety hazards. Selecting materials that are compatible with the fluids and operating condition is essential to prevent corrosion-related issues. The second one is pressure and temperature management. Heat exchanger operate under varying pressure and temperature, which can expose safety risk if not properly controlled. So adequate pressure relief mechanism and temperature control are necessary to ensure safe operation. The third one is chemical and thermal hazards. Some fluid used in heat exchanger may be hazardous or flammable. Proper handling and containment of this fluid are essential to prevent accident and ensure worker safety. Thermal hazards such as a risk of fire or explosion should also be considered in the design and operation of heat exchanger. The last one is energy efficiency and waste heat recovery. Inefficient heat exchanger design can lead to energy wastage and increased greenhouse gas emission. Optimizing heat exchanger performance for energy efficiency and implementing waste heat recovery system can reduce environmental impact and improve overall sustainability.
To summarize, we could say that the design shell and tube heat exchanger are effective for heat transfer. This is because hot oil, 80 degrees Celsius, can be cooled down to 65 degrees Celsius by transferring heat from hot oil by using room temperature water. Furthermore, a heat exchanger's design must take efficiency into account. Lastly, through the case study, we could see that in conjunction with raising the heat transfer coefficient, heat transfer enhancement frequently results in a higher pressure drop. That's all for our group's presentation. Thank you.